Everything you see here is made of atoms. To be specific, the vast majority are hydrogen atoms, the most abundant stuff in the universe. Forged in the aftermath of the Big Bang something around 13.7 billion years ago, it is a product, more or less, of one of the most misleading terms in cosmology today: recombination. This was an epoch of the early universe about 370,000 years after the Big Bang, where the universe cooled sufficiently for electrons and protons to bind and become atoms. At this moment, matter as we know it was born. The reason the word recombination is misleading, however, is that it is a legacy term. There was nothing previous to recombine. The protons and electrons merely combined for the first time, insofar as we think the Big Bang's aftermath unfolded. From this recombination eventually came clumping due to minute temperature differences in the early universe. As that clumping continued, the first stars ignited, which in turn would make elements heavier than the hydrogen, helium, and small amounts of lithium forged by the Big Bang. These heavier elements would go on to become us. While nuclear fusion comes from hydrogen and helium, life itself does not solely do so. Helium is non-reactive and useless, and hydrogen is important, but not on its own. It must combine with heavier elements like oxygen to make water, the solvent of life's chemistry and onward. Our world as we see it here on Earth still bears hydrogen's mark with the oceans, and helium by and large left long ago, with our remaining geologic supply dwindling as we launch our balloons. But the magic really happens with the heavier elements, such as carbon, the basis of our life, all the way to uranium. Forged in stars and supernovae, these heavier elements literally enable us to do everything that we do. Indeed, we are made of these atoms, but so is everything else we see. We eat, drink, and breathe the molecules they form. But this idea of an atom has an unusual history, in that we knew about them long before we actually discovered them. The idea of an indivisible basic particle of matter cropped up in several areas of the world in history, including India and the Greeks. For the Greeks, the idea starts, so far as we know, with someone we know almost nothing about, Leucippus, in the 5th century BC. All we know is that he believed in atoms and was the teacher of the much more famous atomist Democritus, who usually gets the credit. In India, the idea is centuries older, going back to Arunai in the 8th century BC. Subsequently, the idea of everything being made up of atoms was highly contentious. Aristotle, for example, absolutely hated the idea. He would be proven wrong much later, but along with the idea of atoms also came the idea of a void, empty space, something that also held true. Indeed, most of an atom is composed of empty space. But what the protophysicist philosophers of the distant past didn't know was that the atom actually isn't indivisible. It can be split. And that process, nuclear fission, is the first instance where matter can go horribly wrong. This, of course, refers to element 92, uranium, but also extends to plutonium. You can split uranium atoms and produce nuclear energy, but you can also split it and produce an atomic bomb. From there, the question was asked, what else could we do to make bombs out of atoms, which resulted in our first experimentation with what powers the sun itself, fusion. This too was in the form of bombs, but without the ready way to turn it towards energy production. Fusion energy as a viable power source still eludes us. Splitting and fusing atoms serves to point out a certain reality of our universe. It really isn't a universe of matter. That's actually kind of an illusion. What it really is a universe of energy. Born of the energy of the Big Bang, with some of that energy condensing to become matter, but with the option of at least some of that energy being released under certain circumstances, defined by Einstein's infamous E=mc², matter and energy equivalence. Nowhere else does this equation reach its most efficient, as in a matter-antimatter conversion, which results in a 100% conversion of matter to energy. All antimatter is a flipping of charges. An electron, negative in charge, if you change that to a positive charge, it becomes a positron. We make these all the time, and while antimatter is the rarest, most expensive matter on Earth, we can make it. And it does as predicted. It annihilates with normal matter on contact. Whether we can ever use antimatter as a power source is a question for the far future. Production of it, or finding it, may well prove too inefficient for anyone in the universe to ever pursue. As apocalyptic an explosion as antimatter can produce, it simply, so far as we know, is not common enough in the universe to do much in the current times. There may have been a time where it did, however. Some hypotheses state that in the early universe, most of the matter and antimatter annihilated, and there was just a slight bit more matter present for some unknown reason that makes up the universe we see today. But in our times, the biggest reaction we are likely to see involving normal matter and its production is the supernova. This is when a star produces an explosion one way or another. There are several types of supernovae. One is the explosion of a giant star at the last stages of its evolution. Another is when a white dwarf is forced to produce a runaway nuclear fusion reaction. These explosions can be so titanic that they can outshine the entire galaxy they're located in. In 1987, we saw a supernova in a satellite galaxy of the Milky Way, but within our own galaxy proper, it's been a while. But there is an oddity here. The last visible Milky Way supernova was in 1604, known as Kepler's supernova. But it comes just after a previous supernova in 1572. That isn't weird. Estimates based on other galaxies is that we should see a Milky Way supernova about every 50 years. Why there has been such a long gap from 1604 to now is just a fluke, which means we may see one at any time. In a white dwarf-related supernova, this usually happens due to the dwarf accreting material from another star until an explosion of fusion can happen. But in the case of a giant star exploding, this is another instance of matter in a very different state than what we normally see around us. Here, it becomes all about gravity and equilibriums. Giant stars are larger than they would be for their mass because of certain pressures that exist. As a star fuses atoms in its core, it produces huge amounts of energy that radiates out, essentially counteracting the star's own gravity. But as soon as it starts fusing heavier atoms, it gets into heavier metals, and once it hits iron, it can no longer hold its equilibrium, and it suddenly implodes. At this point, material is blown off, sometimes at very high speeds, almost relativistic. A shockwave expands outward, sweeping up even more material from the interstellar medium. Huge amounts of elements are seeded into the universe in this way. What's left after the supernova of the star's core is a matter of its mass. There are different types of supernovae that unfold differently, including one where there is no explosion at all, and the giant star simply collapses directly into a black hole. But what results of supernovae are objects made of very strange forms of matter indeed, neutron stars and black holes. But before we get to that, let's look at the death of the Sun. The Sun does not have the mass to ever go supernova, nor does 97% of the stars in the observable universe. Giant stars are rare, tiny ones common. But at the end of the age of the Sun, when Earth either met its existential end, having been consumed by the Sun's rage as an aged red giant, or left a burned-over cinder, bearing no trace of the technological civilization it once spawned. All that will be left of the Sun will be our white dwarf. The white dwarf stage of a star forces matter as we know it into a different position than it would normally exist in our day-to-day world. A white dwarf is a stellar core remnant. Basically, it's what's left of a star after fusion ceases. A cooling ember under which normal circumstances simply radiates its remaining heat. But it's a compact form of matter. A white dwarf can be roughly the volume of Earth, yet have the mass of a star. But without the radiation and energy of fusion, it can't hold itself up. It has no choice under the laws of gravity to become dense and hot, composed of what's known as electron-degenerate matter. Crushing matter results in very odd effects. The aforementioned nuclear energy, in a nutshell, is hitting atoms with neutron bullets, causing them to shatter. It's not that simple, but it's analogous. An atom bomb in the simplest World War II form was a naval cannon firing and forcing two pieces of uranium together, setting off the fission reaction. In a white dwarf, matter is compacted far further, to the point that electrons orbiting atomic nuclei are forced into their lowest quantum state. They don't like that, so resistance is met. This is called electron degeneracy pressure, and it's the scaffolding that holds a white dwarf up against its own gravity, the next in a series of resistances that define our world. In our normal world, the reason objects are solid at all is partly because of what's called the Pauli exclusion principle. Essentially, no two objects can occupy the same space. The electron doesn't like it. This is why you can't pass through walls or punch your hand through a table in most circumstances. In a white dwarf, these lines begin to blur, because there are limits on just what matter can do. White dwarfs are still made up of atoms as we know them, however. The resistance of electron degeneracy pressure has a limit, a number that can be overcome. On the scale of a star, that number is known as the Chandrasekhar limit, and might be one of the most important numbers in the universe. It is approximately 1.44 solar masses for a non-rotating star, not that much more than our sun's mass right now. Without a power source, a white dwarf cannot exist at a mass above this. So if you start dropping Jupiters into a white dwarf, eventually strange things happen to its constituent matter. For masses above the Chandrasekhar limit, electron degeneracy pressure no longer works, and a further cataclysmic implosion occurs. The white dwarf becomes a neutron star. Here we meet another level of resistance and a completely new form of matter. Here the gravity is so great, the mass so high, that the former protons and electrons of the former atoms that made up the star are crushed. Protons are positively charged, electrons negatively charged. So when you crush them together, the result is a neutron, hence neutron star. This material is known as neutronium, and it's one of the densest and heaviest materials thought to exist in nature. Neutronium is one of those cases in science where someone suggests something that turns out to be outright prophetic, just like the atom. The word neutronium was first coined by a physicist, Andreas von Antropov, in 1926. In this form, it was element 0. This is the actual element 0, having an atomic number of 0 and no protons, rather than the MacGuffin from Mass Effect. The meaning of the word has changed, however, in that the neutron was discovered in 1932, and over time it's come to popularly mean the hypothesized degenerate matter at the core of a neutron star. More shallow areas of neutron stars don't have the pressures needed to maintain this state of matter, only the core. Here's how strange this stuff is. A single teaspoon of degenerate matter like this would weigh 1 trillion kilograms if you could extract it from the core of the neutron star. What holds it up is known as neutron degeneracy pressure, and it too has a limit, which in this case is one of the factors that keeps the neutron star from collapsing into a black hole. But this may be more complicated than merely neutron degenerate material. It has been hypothesized that if you could increase gravity further, you might cause the neutrons to break down into their constituent quarks, forming a quark star. This rare type of star would be even denser, and also smaller than a neutron star. A better term for this kind of star might actually be a hadron star, because that's essentially what it is, a giant hadron. No definitive observation of this type of star has ever been made, thus it remains hypothetical. Another hypothetical related type of star is an electroweak star, which might occur after a supernova. This would be even denser than a quark star, and in a tiny zone where you could crush quarks this much, you might end up with electroweak burning for 10 or so million years that might provide radiation to hold off collapse. Even though quark degeneracy pressure is no longer sufficient to prevent a collapse. But again, there is a limit, hypothetical stars or not. This is the line between anything remotely like a star or former star to something new, a black hole. The limit here is usually termed the Tolman-Oppenheimer-Volkov limit, and it's simply where there are no pressures left in nature that can prevent an object collapsing to infinite density. The singularity at the heart of a black hole. It's difficult at this point to even call it matter, rather something else that formerly was matter. But all of these degenerate forms of matter depend on gravity. What of exotic forms of matter that do not? Or at least not to the same degree? There are many of these, many hypothetical. One that is dependent on gravity, but more like the gravity of Jupiter rather than a star, is metallic hydrogen. This is a solid form of hydrogen, but it may have an odd property. It's thought to be metastable, so if you could extract some of this stuff from the interior of a gas giant, it would hold its form outside of the pressure that created it. Other forms of exotic matter would be negative mass, which would have the property of being anti-gravity. Strange matter, including the infamous gray goo, perhaps one of the most dangerous substances in the universe if it exists, that converts normal matter into strange matter on contact. Lesser known would be exotic atoms, where the normal particles involved in atoms are replaced with other particles of the same charge, such as replacing an electron in an atom with a muon or a pion. Very little is known about what the properties of these exotic atoms might be like, only that all hypothesized forms of them would be unstable and rapidly decay. But it's an interesting thought that entire new classes of atoms might be possible, many with unknown properties. Even stranger is the idea of positronium, where you have a metastable situation where an electron and its antimatter counterpart aren't annihilating, rather orbiting each other. Others include a proton and antiproton orbiting, known as protonium, which is thought to be capable of chemistry, if only for a short time. Then there's antiprotonic helium, where a helium nucleus has an antiproton and an electron orbiting. These all tend to be unstable arrangements, but serve to show how combinations of matter may be possible in the universe very different from our day-to-day matter. How or if these might be used in the far future remains to be seen. Thanks for listening. I am futurist and science fiction author John Michael Godier, currently eyeing all matter in the universe suspiciously, which in itself is suspicious since my eye is made out of matter, so I am an instance of matter viewing itself suspiciously. Very dubious. And be sure to check out my books at your favorite online book retailer and subscribe to my channels for regular in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live.